Hello, and welcome to lesson 16 of this introduction to linear algebra with Wolfram U. The topic of the lesson is the characteristic equation. So let's begin with a brief overview of the lesson. So in the last lesson, we talked about the eigenvalues and eigenvectors for a matrix. And in this lesson, we'll talk about a method for finding the eigenvalues of a matrix. Now, it turns out that the eigenvalues are the roots of a polynomial, and that polynomial is called the characteristic polynomial. So they are the solutions of a polynomial, which we'll now try and show you. So here's the matrix A, for example. It's a 2 by 2 matrix. Then you can work out its characteristic polynomial, which has got a variable lambda. And in this case, it's a quadratic polynomial in lambda. You can solve the equation p equal to 0. You find two values, -3 and 2, and those are exactly the eigenvalues of A. Now, the equation satisfied the eigenvalues is called the characteristic equation. So we have the polynomial and then the equation itself. Okay, so slightly more formal definition. So let's say you have a square matrix A, and if you have an eigenvalue of this matrix, that means that you have the equation AV equal lambda V satisfied for some vector V. And of course, V then is the corresponding eigenvector. Now, this equation can be written as a homogeneous linear system A minus lambda I times V equals 0, where I is the identity matrix. And this equation will have solutions, non-trivial solutions, if and only if the determinant of that left-hand side matrix is 0. So this equation over here is called the characteristic equation for the matrix A. And the eigenvalues are the roots of the equation. And the left-hand side is called the characteristic polynomial of A. So the characteristic polynomial is a determinant which depends upon A and lambda. So as an example, here is a 2 by 2 matrix A. We try and work out its characteristic polynomial directly using det. So you do determinant of A minus lambda I, where that's the identity matrix of order 2. And you can obtain the same answer using characteristic polynomial. You can solve over here, get the roots, and confirm the answer with eigenvalues. You get back just the same answers. You get 7 and -2 over here. Now notice in this case, the roots are real numbers and they are unequal. So as a second example, here is a 3 by 3 matrix. Let's work out its characteristic polynomial. Get the same answer, characteristic polynomial itself. Solve to find the eigenvalues. Check the answer with eigenvalues itself, and you get back two roots which are 7 and one root which is 2, which is exactly what Sol told you a bit earlier. So in this case, you have roots which are real, but a pair of them are equal. And we sometimes would say that the eigenvalue 7 has an algebraic multiplicity of 2. Okay, so some properties of the characteristic polynomial. So it first of all is a polynomial of degree n in lambda, the variable. Now such a polynomial has n roots according to the fundamental theorem of algebra. Of course, you need to count the roots with the correct multiplicities. So if a root is repeated, you need to count it twice. And the roots themselves may either be real and distinct, real and equal, or imaginary, etc. Okay, and the eigenvalues can be found by solving the characteristic equation or by using eigenvalues directly. So, as an example, let's take up triangle matrices again. So you have an upper triangular matrix over here. You see it's 0 below the diagonal. So let's try and work out the characteristic polynomial. But you see over here that the matrix itself is upper triangular. So its determinant is the product of the diagonal elements, and hence the diagonal elements will give you the eigenvalues directly. And so in this case, they are 7, 6, 3, and 1, which are exactly the diagonal entries of the original matrix. So 1, 7, 3, and 6 over here will give you the eigenvalues for this matrix. So you could have an upper or a lower triangle matrix, and you can just read off the eigenvalues by looking at the diagonal entries. Okay, on to another very important idea for this course, and that's the notion of similarity of matrices. So let's say you got two matrices A and B, they are both n by n. We see that A is similar to B if there is a matrix P such that B is P inverse A P, that product over here. And this operation that takes you from A into B is called a similarity transformation. Now the fact is that if you have two similar matrices A and B, then they have the same characteristic polynomial, and hence they also have the same eigenvalues. So similar matrices are important because they have the same eigenvalues. Okay, so as an example, let's start with a really simple matrix, a diagonal matrix with entries 3, 5, and 11 diagonal. So of course the eigenvalues over here are just 3, 5, and 11. Now take up another matrix P, which is non-singular because determinant is not 0, and perform a similarity transformation to get a matrix B. So you get B is inverse of P times A times P. And you notice over here that B itself has the same eigenvalues as A, just as we said early on. And here's another example, but now let's start with the complicated matrix A, compute its eigenvalues, compute the eigenvectors, take the transpose of this matrix over here, and when you do inverse of P times A times P, then you get back a diagonal matrix whose diagonal entries are the eigenvalues of A. So you can start with a complicated matrix and get down to a diagonal matrix by this method. Okay, so that brings me to the end of the lesson, and the point is that in this lesson we've talked about the characteristic polynomial of a square matrix. So the eigenvalues are the solutions of the characteristic equation, which is an algebraic equation in lambda. And if you have two similar matrices, then they have the same eigenvalues. So that brings me to the end of the lesson, and next time we'll use ideas to talk about the diagonalization of matrices. So I'll stop over here. Thank you very much.